Download this code from codegive.com, link in the description below. OK, let's dive deep into the lowest common ancestor of a binary search tree problem on LeetCode. We'll break down the problem, explore different approaches, provide a well-commented code example, and discuss optimizations and follow-up questions. Problem statement, LeetCode 235. Given a binary search tree, BST, find the lowest common ancestor, LCA, of two given nodes in the BST. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. Example asterisk. Understanding the problem. Asterisk binary search tree, BST. This is crucial. A BST has the property that for any node, asterisk, all nodes in its left subtree have values smaller than the node's value. Asterisk, all nodes in its right subtree have values larger than the node's value. Asterisk, lowest common ancestor, LCA. The LCA of two nodes P and Q is the deepest node in the tree that is an ancestor of both P and Q. An ancestor can be the node itself. Asterisk, important implication of the BST property. Asterisk, the BST property allows us to efficiently search for P and Q and to navigate the tree strategically to find their LCA. We don't need to traverse the entire tree blindly. Key ideas and approaches. 1. Iterative approach, most efficient. Asterisk, this is usually the preferred method due to its efficiency, both time and space complexity. It leverages the BST property directly. Asterisk, start at the root of the BST. Asterisk, while the current node is not the LCA, compare the values of P and Q with the current node's value. Asterisk, if both P and Q have values smaller than the current node, move to the left subtree, since the LCA must be in the left subtree. Asterisk, if both P and Q have values larger than the current node, move to the right subtree, since the LCA must be in the right subtree. Asterisk, if P and Q are on different sides of the current node, one smaller, one larger, or if one of them is the current node, then the current node is the LCA. 2. Recursive approach. Asterisk, similar logic to the iterative approach, but implemented using recursion. Asterisk, base case, if the current node is null, return null. Asterisk, recursive steps. Asterisk, if both P and Q are smaller, recursively search in the left subtree. Asterisk, if both P and Q are larger, recursively search in the right subtree. Asterisk, otherwise, the current node is the LCA. 3. General binary tree LCA, less efficient, not exploiting BST property. Asterisk, this is a solution that works for any binary tree, not just BSTs. This method doesn't take advantage of the sorting property of the BST and will be less efficient. This method is included here for comparison to show how much better a BST-specific solution can be. Asterisk, the general LCA approach for a binary tree involves the following steps. 1. If root is null, return null. 2. If root is one of P or Q, return root. 3. Recursively search in the left subtree for P and Q. 4. Recursively search in the right subtree for P and Q. 5. If one of P or Q is found on the left subtree, and the other is on the right subtree, then the current root is the LCA. 6. If both P and Q are in the left subtree, then the LCA is in the left subtree. 7. If both P and Q are in the right subtree, then the LCA is in the right subtree. Code example, iterative, most efficient. Code example, recursive. Code example, general binary tree LCA, less efficient. Explanation of the iterative code, most efficient. 1. Initialization ** current starts at the root of the BST. 2 While loop asterisk the loop continues as long as current is not null. 3 Comparison asterisk. Asterisk p.val current.val and q.val current.val, if both p and q have values smaller than the current node, it means the LCA must be in the left subtree. So, we move current to current.left. Asterisk p.val current.val and q.val current.val, if both p and q have values greater than the current node, the LCA must be in the right subtree. We move current to current.right. Asterisk else, this is the crucial part. If the previous two conditions are not met, it means that p and q are on different sides of the current node, or one of them is the current node. In either case, current is the LCA. For return asterisk we return the current node, which is the LCA. Time and space complexity. Asterisk iterative approach, most efficient. Asterisk time complexity asterisk O, H, where H is the height of the BST. In the best case, balanced BST, H equals log n, where n is the number of nodes. In the worst case, skewed BST, H equals n. Asterisk space complexity asterisk O, 1, constant space, we're only using a few variables. Asterisk recursive approach asterisk. Asterisk time complexity asterisk O, H, where H is the height of the BST, same as iterative. Asterisk space complexity asterisk O, H, in the worst case, due to the call stack during recursion. In a balanced BST, the space complexity is O, log n, but in a skewed tree, it can be O, n. Asterisk general binary tree LCA asterisk. Asterisk time complexity asterisk O, n, in the worst case, where n is the number of nodes in the tree. This is because, in the worst case, we might have to visit all nodes in the tree. Asterisk space complexity asterisk O, H, in the worst case, skewed tree, where H is the height of the tree, due to the recursion stack. O, log n, for a balanced tree. Why is the iterative approach preferred? The iterative approach is generally preferred because asterisk space efficiency asterisk it uses constant space, O, 1, while the recursive approach uses O, H, space due to the call stack. This can be significant for very large trees. Asterisk often faster in practice asterisk although both have the same theoretical time complexity, iterative solutions often perform slightly better in practice due to the overhead of function calls in recursion. Important considerations and follow-up questions. 1. Assumptions asterisk the problem usually assumes asterisk the BST is valid. Asterisk both P and Q are guaranteed to be present in the BST. If not, you need to handle those cases, example return null if P or Q is not found. 2. P or Q is the LCA asterisk remember that the problem definition allows a node to be a descendant of itself. If P is an ancestor of Q, or vice versa, then P, or Q, is the LCA. The code handles this correctly because when one node's value equals the current node, the else condition triggers, and that node is returned as the LCA. 3. Null check on root asterisk always include a null check at the beginning to handle the case where the tree is empty, root equals null. 4. Non-BST asterisk if the tree is not a BST, you cannot use the efficient iterative or recursive solutions that leverage the BST property. You'll need to use the more general tree traversal approach, as shown in the third code example, which has a higher time complexity. 5. What if P or Q don't exist? The problem constraints often state that both P and Q exist. If this were not the case, you'd add checks to verify their existence. Here is an example using the iterative version. This adds an initial verification step that P and Q exist in the tree before proceeding with the LCA calculation. In summary, the lowest common ancestor of a binary search tree problem is a great example of how leveraging the properties of a data structure, in this case, the BST property, can lead to a very efficient solution. The iterative approach is generally preferred for its space efficiency and practical performance. Remember to consider edge cases and assumptions when implementing your solution. Good luck.